Excuse me. Hi, welcome back. So, today we are going to be deriving the Leibniz rule for integration, which, between you and me, it's basically just the Feynman rule, but we're just going to be doing that today, so let's get to it. Alright, so what the Leibniz rule of integration, or Feynman rule of integration says, is that if you take the derivative with respect to t of some integral from a to b of some arbitrary function of x and t with respect to x, well, it tells you that you can bring that differential inside the integral. So it's called differentiating under the integral sign, which gives you some integral from a to b. And because you're working with two independent variables, you are going to be using partial derivatives. So bring that inside, you have a partial derivative with respect to t of our function x t with respect to x. So that's what it says. Now what we want to do is prove that. So what we first want to do is set some function equal to our arbitrary function that we're going to be integrating. So that means we're going to have some I value, we'll call it, of x and t, and that is going to be equal to our interval from a to b of our arbitrary function of x and t with respect to x. Okay, so now what we want to do is take the derivative of this function now. So we're going to take the derivative of our I function, x and t, and that is going to give us our limit definition of this integral here. But we want to have the limit definition of our I function, our I variable that we're going to be using here. So that's going to be put together by using the difference quotient. So we're going to have our limit as delta t approaches 0, and we are going to take our I value, and that is going to be composed with our x comma t plus delta t, which is minus f, or sorry, not f, it's going to be I of x comma t divided by delta t. Okay, so we have that. Now what we want to do is construct our limit definition of this function right here. And to do that, we need to adjust our boundaries. So what we're going to have is this equal to our limit as delta t approaches 0, and our limit definition here we're going to have here. So our boundaries are going to be going from a plus delta a to b plus delta b now. So a plus delta a with b plus delta b. And our inside variable is just going to be nothing but, first of all, I'm going to parentheses this off real quick. So our function as a function of x comma t plus delta t with respect to x. And we are going to be subtracting from our a to b boundaries. So we're going to have a and b, and that is nothing but our function as a function of x and t with respect to x. And just as a reminder, we're also including 1 over delta t here. That's what we're going to be multiplying. We're just factoring that out for now to make this look a little bit neater. So we're going to apply the linearity rules of integration with respect to our boundaries here. So we're going to decompose that, and that is going to look like, so we start at, so we got our limit, delta t, delta t to 0. And to begin, we start with our limit, where our initial point is going to be from a plus delta a all the way to a. Okay? And that is going to be our function of x comma t plus delta t with respect to x. And we're going to be adding that with our next one going from a to b. So now we're going to go from a to b of our function of x comma t plus delta t with respect to x. And I'm going to expand this out a little bit. And then we're going to be adding from b to b plus delta b. So here from b all the way to b plus delta b. And then that's going to be of our function x comma t plus delta t right there. Okay? And then of course we have to make sure that we are subtracting from our final point of our function of x and t. So we're going to have this from a to b of our function composed with x and t with respect to x. And to keep expanding this out here, so this is going to be parentheses off. And remember, we still have that 1 over delta t here. Okay, now how we want to rearrange this a little bit. We want to adjust the boundary of this first factor here. We want to multiply it by -1 so we can reverse the boundaries and then rearrange these a little bit. So let's do that. So to do that, we're going to have our limit of delta t approaching 0, and starting from this point, we're going to have 1 over delta t, the parentheses here, and then we're going to begin with our first set. So from a to b of our function composed with x comma t plus delta t with respect to x, and that is going to be subtracted from our next part, which is our end value, our end integral that we're subtracting everything else from. So we're going to move this over there. So we're going to have from a to b of our function x and t with respect to x. And because we multiplied our first term here by -1, remember that reverses our boundaries, but it's also a negative. So that means we're going to have this all of this here added to delta, or b from b plus delta b, where we have our function of x comma t plus delta t with respect to x. And as I said, now this factor is negative, so we're going to be subtracting from a to value a plus delta a. And that is going to be our function composed with x comma t plus delta t with respect to x. Okay, so now we need to reach into our grab bag and use some of the other tricks that we've learned in calculus, specifically Calc 2, and some of Calc 1 as well. So what we're going to need to define before we do anything with this is the fundamental theorem of calculus 1, not 2. So we're going to define that real quick. Fundamental theorem of calculus 1, which simply just states that we have some integral from a to b, some arbitrary function, with respect to x is equal to our function evaluated at b subtracted from our function evaluated at a. Now, pretty simple. You should all know that. Not too difficult. Now, another concept that you may have learned in Calc 1 and some of Calc 2 as well is the mean value theorem. So what we're going to define to be the mean value theorem, oops, that is not an M. So the mean value theorem. Well, what that simply just states is that if you have some curve along a plane, some arbitrary curve going from point A to B, well, you're going to have some C value, kind of some constant, smack dab right in the middle there. And when you evaluate the integral between them and divide by the difference between them, then you're just going to have, well, actually what you're going to start out with is just a secant line going between B and A here. And then as you evaluate it, it shrinks the interval and the margin gets smaller and smaller, and you'll end up sort of osculating a plane with this tangent line here. So that's simply all that is. Now, to define that, we're going to have our f evaluated at c is equal to our function of b and our function evaluated at a divided by b minus a. Now, this is actually pretty similar to that. So our mean value theorem is pretty similar here. So these bear some resemblances. So we can actually do a little bit of manipulation to set them equal to each other. So what that looks like is if we were to define our function from the fundamental theorem of calculus, composed of b, minus our function composed of a, well, we can simply just set that equal to, well, we can actually put our function as evaluated at c here and multiply it by b minus a. And if you work that out, you'll see that these b minus a's cancel. These two are in fact equivalent. So now, keeping that in mind, we can actually start using this definition to define some of these terms here. Specifically, we're gonna take this one with us here. All right. So we're going to define this first. So we're going to have our function where we have, some b value from b to b plus delta b of our function of x comma t plus delta t with respect to x. Well, that we can sort of composite with this sort of formulation here. We know that this has to follow the fundamental theorem of calculus. So therefore, we can set these two equal, where we have our function of b plus delta b, and then our time variable as well, and that is going to be subtracted from our initial boundary condition, which is going to be b and t. Now, we can generalize it using the proof we just showed. So we can set that equal to some function evaluated at a constant, right? Evaluated at some constant, where we are going to have simply just b minus a. But in this case, we're going to have b plus delta b minus b. Okay, so this is incredibly helpful. This is finally getting to the end here, so bear with me. So at this point, what we want to do is evaluate the limit of what we just proved here. So we're going to evaluate the limit and reduce that margin down as much as possible. But first, I've just neglected to do one minor detail. Cancel these b's. We can get rid of those b's, no problem. So this is just going to end up looking like f of c, times delta b. That is what we're going to take the limit of. So let's take the limit. As delta t approaches 0, and we're going to do that with respect to our function of some constant here, times delta b. Oh, I'm sorry. There should be a t here. I forgot to include that. We need to include our time variable if this is going to work. So that's delta b. So just remember, there should be a t variable there. Apologies. So this is going to be equal to, well, what does that value sort of converge on after you evaluate this limit as t approaches 0? Well, given the fact that it's as the t variable goes to 0, it's going to shrink that interval down, but you're also multiplying by delta b. So you're going to reduce that margin between the beginning variable, which b starts, and then the initial. So you're going to have our f of b, comma t, and that is times delta b. Okay, so now we don't have to go through that whole process for this term here. We don't have to, so for this one, we know that if we just take the limit as delta t approaches 0 of our f of c, comma t, times delta a now, that is going to, of course, be equal to our function evaluated at a, comma t, times delta a. So, there. We're just about there. So now we just need to substitute these in to our proof that we have over here. So we are going to, I'm going to write this all out again, so like I said, bear with me. So we're going to have our limit as delta t approaches 0, and we're going to have 1 over delta t on the outside here, and we're multiplying this all now. So we're going to have this from a to b, and we can actually just merge the two factors here together. So that's what we're going to do. We're going to take these two and just bring them together because they have the same boundary conditions. Therefore, they can be treated as the same here. So we can have our function of x, t plus delta t minus our function evaluated at x, comma t, and that is with respect to x. Now, substituting what we have here in for what we just solved for. So now we can add our function of b, comma t times delta b minus our function of a, comma t times delta a. And now all we really need to do is multiply everything by that factor of delta t, bring that all over, and then take the limit. So what that gives us is we're evaluating the limit, so I don't need to do that. So what this ends up being is our a to b of our, essentially our difference quotient of our arbitrary function that we chose to represent, of t plus delta t minus our function of x, comma t That's all over delta t. And this is with respect to x. And this is added to our function of b comma t, where we have delta b over delta t minus our function of a, oops, that's not an a, of our a function or variable and t times delta a over delta t. Okay, I said I was going to evaluate the limit. I lied, but now once I evaluate the limit, as that approaches 0, well, this just becomes our partial, where we have our integral from a to b of some arbitrary, well, of our differential, our partial differential, with respect to t, times our function of x comma t, with respect to x, plus our function of b comma t, where we have now just db, because these now become differentials, with respect to b, or with respect to t, minus our function evaluated at a comma t, where we have dA over dt. And there we have it. As we set out to prove, we have now proven it, the Leibniz rule of integration, which effectively is just the Feynman rule, but, you know, beggars can't be choosers, I guess. So, well, thanks again for watching, and please subscribe if you want to see more like this in the future. Thanks.